solve the following exact ODE. This one, we can think this one like m as a function of xy, n as a function of xy. And we know that when we have m as a function of xy, m dx plus n dy equals 0, this ODE, this differential equation, is an exact if we find this is exact if and only if, in fact both ways, parcel of m with respect to y is same as parcel of n with respect to x. Okay, if they are same, this is exact. But it's already given exact, so we don't have to check. But if we check anyways, let's find parcel of m with respect to y. This is 0 because there is no y, 0. This one is 1 over x times y, right? 1 over x times parcel of y is 1. So simply 1 over x. And this one n x with respect to x. Natural log of x is 1 over x minus this one is just the y. So with respect to x is 0. So 1 over x. Okay, they are equal. But this one was not needed, so I would not even write anymore. Anyway, this ODE, this differential equation is given exact. Now we need to solve, find the solution. So from the definition, when this is an exact, we can find one function. There exists a function, let's say uppercase f, as a function of xy, such that when we find parcel of f with respect to x, partial derivative of this function with respect to x, we get m 1 plus e raised to 2x plus 1 over xy. So let me put in this way, y over x is 1 over xy. I'm going to call equation 1, and parcel of f with respect to y will be n, which is natural log of x minus cosine y. Okay, this happens when the ODE is an exact. Then we can find a function with these two properties. And by the way, the solution at the end of the day will be the function equals some constant. This function is a function of xy. Okay, that's the final answer. Now we have the partial derivative of f with respect to x is this, parcel of f with respect to y is this, but we need the function back. So we can integrate this with respect to x or integrate this with respect to y. It's up to us. Generally we take the easier one, maybe number 2, because this one is kind of only 2 terms. Let's integrate with respect to y. So integrate 2, that's the y, so with respect to y. Then we get the function back, by the way. Okay, when we integrate, that's the fy, so we get the f back equals integrate with respect to y. So let me set this up. This is kind of partial antiderivative. You can write regular d, but I'm writing in this way. With respect to y, this ln x is constant. Then what is 2 dy? When we have a constant dy, the antiderivative is 2y. Right? That's the same as ln x is constant, so y. Minus antiderivative of cosine is sine y. Plus constant of integration. But x could be also a constant in this case, because we are finding function of, we are integrating with respect to y. So it can be some function of x. This one is also constant in this case. So that's the function. 3. The solution, as I said earlier, is a function equals constant. The function is almost there, but there is h. That's the constant of integration in this case. Constant of integration with respect to partial, this derivative. Okay. Now we need to determine h. So we haven't used 1 yet. So this is the function. So I want to get fx here too. This is function. So find the parcel of 3 with respect to x. Okay. So differentiate 3 with respect to x so that we can compare with 1. So this will be f x partial with respect to x. This y is constant in this case. So derivative of natural log of x is 1 over x and y constant minus derivative of sine y is 0 with respect to x. So there is no x here plus now the derivative, right? It's the only one function. I mean single variable, so regular derivative. That's equations are. Now let's compare 1 and 4. Okay, our goal is to determine h in the equation 3 because the solution is function equals c. The function is almost there, but we are trying to find h. When we compare by design the left hand side fx, they are same. Fx means partial derivative of f with respect to x. In the right side though, 1, there is no 1. 1 over xy, 1 over xy. So we have the same. Okay, this one is same here. That means this one left over, 1 plus e raised to 2x should be equal to minus 0, does not count, h prime x. Okay, so comparing 1 and 4, equation 1 and 4, we get what? This one equals h prime x. So let me write h prime x equals 1 plus e raised to 2x. From here, we should be able to find the function h. So now we integrate regular integration with respect to x. 1 plus e raised to 2x with respect to x, and antiderivative of 1 is x plus antiderivative of e to x is itself, but there is a 2, so we need to divide by 2 plus some constant, but our final answer will be the function equals c, so that this constant will be observed, so I don't have to write anything. Thus the solution of the exact ODE is the function equals c, some constant, and the function was found in 3. Look at 3 here. Okay, that is ln x y minus sine y plus hx we found here. H is plus x plus 1/2 e raised to 2x. Okay, this is essentially the same thing, 1/2 e raised to 2x, that equals c. Okay, this is parenthesis here, ln x times y, this one, final.